Okay. All right. Let's just start today's class. In today's class, we are going to talk about long context LLMs. By long context, it means that we mean usually when we train a model, we have a fixed context window, right? For example, like 2048 token. That's for one. That's how large a single prompt can be. But like when you are training a model like with a small window size, when the model sees a larger prompt, what will happen? Um, so when you are enter a prompt that's larger than the original trained context size, one thing is that if you are using this um, positioning encoder, then suddenly the model sees a position that it never sees before, right? In that case, the model will crash. So so in this lecture, we basically talk about a bunch of techniques trying to make the models that's trained with a small context window size to tolerate, to accept prompts that's much larger than was originally planned to use. Here is a overview of the topics we are going to cover for this lecture. So first, we are going to talk about the context extension. We are going to review the rotary position and embedding. We talked about this previously. We're going to talk about how to fine tune the large language model when we are accepting a larger context. We are going to talk about benchmarking long context large language models. We are going to talk about a couple of efficient attention mechanisms, especially when we are accepting a much longer context. The attention is going to explode, right? How to further I know we talked about a lot of different attention compression techniques, but the KV compression techniques, but we are going to talk about a couple of more optimization techniques when we were accepting a larger context. And finally, we are going to talk about a new model trying to replace transformer. All right, so first let's take a quick recap of this rotary positional encoding. So we explained this previously, so I'm going to, just a quick review of what's happening here. So in rotary positional encoding, instead of assigning a absolute positioning to each token, we divide all these input tokens into pairs. Let's say like we divided the embedding of dimension d into d divided by two pairs. So each pair has two numbers, right? And for each pair, we are rotate this pair by a angle theta. And then like for the second pair, we are rotating this by theta 2. And how do we get the theta? The theta is calculated with this equation. So each pair is going to be rotated by a different degree. Does that make sense? And then like for the second token, in the window, we are going to rotate the first pair by 2 theta 1, and the second pair by 2 theta 2. Okay, and doing this for each token here. So we get all these tokens with the positioning and coding. Any questions? Okay, so why this rotary position encoding work? It's because when you are doing the inner product of these two vector over here, So when you do inner product of these two vectors, so for example, when you are doing the attention operation, right? The if the first vector has a relatively position m and the second one has a relative position n, then after doing the product, the inner product, it's actually automatically encoded as the product of q and the k, this two original encoding with a positioning encoding n minus n. So by doing this relatively distance of these two encoding are automatically calculated. Okay. So another benefit of doing this rotary positioning encoding is that because this one, even when, for example, even when we were training this model with the 2048 window size, when you see a token that's coming after 2048, let's say 2049, we still do know how to encode the position because essentially we just keep rotating these different pairs, right? You guys seems confused. Do you guys are you clear about how to do the rotating here? Okay, so let me try to explain this with a little bit more detail. So first of all, let's look at this enhanced, and then this whole vector here. So this whole vector is the embedding for the word enhanced. Okay, so let's say enhance the transformer with rotary positioning and embedding. Okay, so let's say this is the prompt, right? So this is the prompt. This is input to the model. So we are and all these enhancer has a encoding, right? This is a token for the enhanced. So that's not a problem, right? So there's no problem here. And then we are dividing this token into pairs. So and every two number as a pair. Okay, so we have so many different pairs. So far, so good. Once we have one pair, let's say this is a green pair, and two number, and we are treating this pair as a coordinate in this coordinate. So we are treating this pair as a vector on this coordinate. Does that make sense? Okay, so therefore, for this token, we are going to have d divided by 2 vectors, right? Right, on this, in this coordinate, okay? And then for each vector over here, we are rotate this vector by theta degree. Okay, so for example, let's say here, originally it's x1 and x2. Okay, after the rotation, the new pair becomes x1 prime and x2 prime. Right, and we can do the rotation, of course, like by multiply with another vector. Does that make sense? So you can multiply this original one with a vector to get a new vector. And that vector you're multiplying kind of indicates the degree of this shifting, this rotation here. Does that make sense? Okay, so we are rotate this by theta, the first pair by theta 1. Okay, and then for the second, well, for the first pair of this transformer, we are rotating this vector by 2 theta. So we rotate a little bit more. Okay, and then for the width, we are rotating 3 theta. The rotary rotated by 4 theta, 5 theta, and 6 theta. Does that make sense? Does that make sense? Okay, so there's one problem. So when you are doing this, if the theta is very big, what will happen is at a certain point, the vector is going to overlap. Because basically when you're rotating it, it's kind of like just rotating over this, right? And if the theta is very big, then it's soon just like your watch, the second hand, is going to overlap soon. Does that make sense? So therefore, for the second pair, the theta 2, for the second pair, we are going to rotate by a different degree. Okay? So then like theta 2, 2 theta 2, 3 theta 2, 4, and 6 theta 2. Okay? But how do you derive this theta 1 and 2 and 3? It's derived by this equation, which basically says theta equals to this is 10,000. Wow, this is basically it's 1 over 10,000 power to 2 this divided by d. Right? Right? And what's the relationship among these thetas? So we can see that when the pair, when the index is larger, when the I is larger, basically the theta I is going to be what? If I is larger, theta I is going to be smaller, right? So therefore, each pair actually is rotating by smaller and smaller degree. Does that make sense? Okay. So, but then like basically we are going to see a bunch of new vectors that's rotated by different degrees. Okay. All good so far? And then basically says, when we are and we are using this kind of degree, a bunch of degrees, to encode the position of this token inside this sequence. Okay, that's how we do this. And when you are doing a inner product, of these two token with the relatively positioning, it equals to the original token inner product with this m minus n embedded in the encoding. Does that make sense? And therefore, the inner product, when we are doing the attention between these two tokens, the relatively distance among these two tokens are automatically captured. Does that make sense? Better? Okay. So the benefit of this is that, well, there are two main benefits. So one, why we are talking about this, one benefit is that if the original model was trained with a context window as 2048, and then like when you are entering a prompt that's much larger than 2048, if we were using a absolute positioning encoding, we don't have any more positioning to assign to those extra tokens. Does that make sense? But in this case, we are fine because basically we just keep rotating this to get the new positions. We don't need it like this 2048 absolute positions. Does that make sense? Because we can just keep rotating these vectors to get a new relatively position. Okay, that's the first benefit. The second benefit is this. The second benefit is if we were having a larger context window, we can simply dividing the theta by 2. Then suddenly we have more positions to assign to these new tokens. Okay. So that's the why like most of current models are using this rotary positioning encoding instead of the absolute positioning encoding. Okay. So that solves the positioning encoding problem. So second, this long LoRa, what it does is trying to do is that, well, if original is trained on this small window size, when you are feeding a larger, we need to tune. We want to like tune the model to accept the longer context window. Okay. So basically, this one says, if you are, if Llama 2, say like Llama 2 was trained with 2048 tokens, and suddenly you are giving the whole Harry Potter and Chamber of the Secrets book, this whole book to the model. It does not know how to do this because it has like 40K, 30K tokens. Okay. And it'll just give you the wrong output because I don't know, like, I'm sorry, originally was trained with 4,096 tokens. Now I have 30K tokens. I don't know how to handle it, right? Well, one way is that I'm going to just retune this whole model with this 30K token. But we know that if you were trying to accept a more context window, if you are trying to accept a larger context window, then the attention size, the attention table is going to increase significantly, right? Because it's a 2D table. So it's going to need to build do this 30K by 30K attention table. Does that make sense? So it's going to need like so many, so it's basically the training cost is very big. So this long LoRa work is trying to see how we can tune the original model to accept more tokens without fully train this whole model. Okay. So the idea of this long LoRa is that it's going to split the attention heads. So when I'm tuning the model, now I have like a lot of tokens. I'm going to split the attention heads. Let's say like I think the Llama 2 has 64 attention heads. So I'm going to split to 32 and 32. Okay. And also I'm going to group the tokens. Okay. So instead of like, 30K by 30K, I'm going to just group them into small groups. And in this 32 heads, I'm going to only do attention with this nearby tokens within this single group instead of do this full attention. Okay. But that gives you a problem, right? So if we are only doing the attention within single group, you are not exchange the information across these groups. Does that make sense? If we were only, tuning the model with only doing attention within each single group, then the information across different groups are not exchanged. Does that make sense? Okay. So therefore, to fix that, the paper proposed, like within the other 32 heads, we are going to shift the pattern a little bit. Instead of this, I'm going to group these tokens together. Okay, and doing the attention. Okay, and then like after this 32 heads, another 32 heads. Finally, I'm going to combine all these attention values together. So in this way, you can see that we are going to exchange information across the adjacent groups. So this one gives you a little bit more explanation. So this one gives you this, let's say we have 4 heads, 1, 2, 3, 4. And then we have 1 to 8 tokens. But while in reality, we are trying to tune the model with 64 heads with 30K tokens, right? Okay, all good, all good. So this one, we just illustrate the idea. So we are going to split the heads into half and half, okay? And within this half, I'm going to group, let's say I'm going to group 1 and 2 together and to do cross attention. I'm not going to do full attention across this 1 to 8 and 1 to 8. I'm only do attention between 1 and 2, 3, 4, 5, 6, and 7, 8. Okay. And on the other half of the heads, I'm going to shift a little bit, and I'm going to do attention with 8 and 1, 2, 3, 4, 5, and 6 and 7. Okay. So in this way, half of the, and then I'm going to combine them together. So in this way, I'm trying to exchange the information across these adjacent groups. So now, basically, we got attention information from 1, 2, and 1, 8. Does that make sense? Okay. And then we are repeating this process many layers so that all the information from all the tokens are exchanged. Does that make sense? So that's this long LoRa. Another thing that it's proposing is that it's going to fine tune. So when you are tuning the weights, instead of tuning the original weights, it has a low rank matrix. We only tune this low rank matrix. Okay, so I don't know if you are familiar with the LoRa. Basically, you have a smaller matrix that's being tuned. And this paper find out that in addition to fine tune the attention weights, all these QKV matrix weights, you also need to tune the normalization and the embedding. But happens to these two, all these weights are relatively small compared to the QKV matrices. Okay. And during the inference, like if you have a longer context, we are going to do the full attention during the inference. So one thing I want to mention here is that the different pattern happens like across different heads, right? So let me try to draw this because you guys still seems like a little bit confused. So basically, when we are tune this model, when tune this model with a larger context window, we are splitting, let's say like this is 32 heads, this is 32 heads. Okay. And inside these 32 heads, we have a much larger attention map, right? Let's say originally it was 48, 496. Let's say just 4K. Originally the attention is was trained with 4K by 4K attention. Does that make sense? Now we have 30K by 30K. I'm sorry, oh, this is 32, but this 30K by 30K. So the tune cost is way too much. So that's why we are doing this, we only divide them into small groups. And we are only doing the cross attention within these small groups. Okay, and then for the other 32 heads, we are shifting the pattern a little bit. Okay, so we are and doing the self-attention within these groups. And then these two, the 32 heads and 32 heads are going to be combined, passed to the next layer. Does that make sense? So in this way, we are trying to mix the information across different groups. Okay, is that better? Okay. So we see that like by tuning the model with a larger context window, we can reduce the perplexity, almost the same as like full fine tune. Okay, and also like this one shows the training hours, and this long LoRa gives you. We can see that if you have a full fine tuning, the hour is much larger than this long LoRa. This one is trying to show that this one basically is trying to show that by tuning both the weight as well as the normalized norm and the embedding, we can reduce it's important, and we can reduce the perplexity to be almost the same as the full fine tuning. And this one is trying to do this topic retrieval on long chat to see, like, after the long tuning, are you really able to retrieve the information from the long context? And the experiment results basically shows that it does improve the capability to retrieve the information from the long window. Okay, so then like we want to cover the evaluation of the long context large language model. So we want to know, like, how do language model use the context, there's a very interesting phenomenon called loss in the middle. So the model shows a U-shaped performance curve. So this is the let's say this is the length of the context. Totally, we have a 4K token, and this one, the x-axis shows the position of the document within with the actual answer, and this shows the accuracy. So what this figure is trying to show that when you have a really long context, and if the answer you are looking for in different location of the context window, the accuracy is actually different. If the document with the answer is in the early location, the early locations, the accuracy is going to be high. If the if the document with the answer also like in the later location positions, the accuracy is high. But if the document with the answer is in the middle of the whole window, the accuracy actually is going to be low. So this is called this loss in the middle phenomenon. Okay, the key insight is that the fluent long context response doesn't imply effective long context processing. The location of the document with the answer really matters to the accuracy. So we have a couple of different um, ways of evaluating the performance when the context window becomes really long. Okay, so this is one way is to do is so-called needle in the haystack. So what it does is that it's inserting the information, the needle, at different depths of a long document. Okay, so for example, let's say like the best thing in San Francisco is eating a sandwich and sitting in the Dolores Park on a sunny day. Okay, and then ask the model at the end of the document to record the information, like what is the best thing to do in San Francisco. Okay, when we are, and then like we are placing this answer into different locations of this long context, and let's see the performance. Okay, the x-axis is the context length. The y-axis is the placement, the depth of the document of this this answer. Okay, so let's see what we are asking GPT-4 128K to retrieve this information. So what we can see here is that when let's say like when the context length is relatively small, let's say like smaller than 64K, the model can always retrieve the correct answer. But when we are keeping the context window like double it to 128K, then you can see that, well, if you are placing the document at the top of the if you are placing the needle, basically the answer, on top of the document, it's green. And if you are placing, to the bottom of the document, it's also like relatively accurate. But if you are placing the needle in the middle of this context, you start to see accuracy drop. Does that make sense? So this is and then we are basically using this kind of to trying to see how good a model is to fetch the needle from the haystack. But that synthetic data set has limited real-world relevance. So this long benchmark includes 21 data sets across like different tasks, supports context up to 13K tokens. And they evaluated different large models. They find out techniques like scaled position embedding improve the long context understanding. Retrieval and context compression helps, but not as effective as models inherently designed for long context. So the retrieval and the context compression are the things that we mentioned as RAG, retrieval augmented generation. So if you so it's not as effective as if you have a model that's just itself can tolerate a lot of tokens. Next, I want to talk about efficient attention mechanisms. So this is a recap of the KV cache. I think this is we have seen this a couple of times, and basically the KV cache is going to increase significantly with the this one is the batch size. Okay, so next I want to talk about a interesting case of long context, which is the chat. So if you think about it, like so far when we're asking ChatGPT a question, usually you give a prompt, give you the answer, right? But if you want to like really develop a chatbot, means that like you keep like multiple rounds of conversation, and this rounds of conversation basically can go infinitely long, right? Right? It means that like, it can get like really long. So when this if the chat history becomes like really long, what should we do? The biggest problem, like if we were keeping all these KV cache, then the KV cache is just keep growing, right? And we know like we only have a limited memory. And if the KV cache exceeds the memory limit, what should we do? The most intuitive approach is what? The most, well, if you are, if not like if you are keep carrying out a multiple round conversation with the chatbot, okay, with the large language model, instead of just ask a one time question, then like we need to keep a really long history, and not just that, but also you keep asking questions, and it's going to keep growing, right? And we know we have a limited memory size. What should we do? Like to process this kind of like infinite long input. Yes.
Should you remove the oldest values from cache? The newest one?
So I'm sorry, say that again.
So remove the oldest values.
So that's the most intuitive, like a cache, right? We use the memory as a cache. So we remove the old, only remember the most recent, because the idea is that, well, the idea is that only the most recent conversation will matter more than the early tokens, right? Right? So that's the idea. Okay. So, well, apparently that's what people thought initially. If we do not do that, then we will be, out of memory, and the performance breaks. Okay. But even if we do that, like this so-called like this windowed attention is exactly the idea you mentioned. So we just keep a window. Okay. And all these previous tokens, we are going to discard them because that's all we can hold. Okay. Okay. So that's that. But if we are doing this so-called window attention, what people find out is that so the x-axis is the input length, the y-axis is the perplexity, and where's the window? So this is the dense attention. This is the window. The orange one is the window attention. So let's focusing on the window attention. And we can see that the window attention suddenly has a perplexity jump. Means that like model basically crashed. It does not know the correct answer anymore. Okay. And where is the line? The line is the KV cache size. Okay. What that means is that if we were using the window attention, just keep discarding it, then immediately after the chat history is larger than the KV cache size, the perplexity increases. Means that the window attention mechanism is not going to work. It's not going to work. But why? But why, right? So people find out that's not going to work. Why? But the people find out like, if not like, if I'm using a window, but do recomputation, the perplexity actually will come back. What does that mean? So what's the difference between this, simple window and the window with recomputation? So the simple window attention basically says, well, for all the previous tokens, all these keys and the values, we just calculated once, so we just keep it going, right? And once we exceed the memory size, we just remove all these previous tokens. This is not going to work. Okay. But the recomputation means that, well, now I only have this window size. I'm going to recalculate all these keys and the values for this window size. Then this actually works. Do you understand the difference here? Okay. So the difference is that now we recalculate all the keys and the values. So people think, oh, why is that? But if you do the recalculation for the window, the overhead actually is quite big. Because the whole point of KV cache is that we just calculate all those keys and the values for the previous tokens once. We don't want to keep recalculating them. And the recomputation basically is keep recalculating them, right? But why this recalculating will work, but I'm just using the older cache will not work. Yes.
If you just remove, then you lose the information, like probability information from when you just remove the initial tokens, but if you recompute, then the probability redistribute.
So let me we have an eraser here. Okay. So basically it says, wow, if you are chatting with the chatbot, right? So this is okay, this is your conversation, right? If and when we are doing, when the if we are just doing a window with a windowed attention, then the model calculates the prompt, okay, all the keys and the values of all those tokens, and calculate also like its own answer, right? And then your prompt and its answer, right? And then when the memory is not big enough, I'm going to discard all the KVs for the previous one. I'm only keep this. But I'm not recalculating all the Ks and the Vs when I have a new question, right? So the recompute means that, well, every time like I have a new answer, I'm going to get this whole size. I'm going to recalculate all those KVs and do the generation. Does that make sense? But this recalculation will work, but this just keep the older ones will not work. So what's the difference? When we are recalculating the keys and the values and all this, what's additional information that's actually what helps? So what people find out is that this so-called like attention sink phenomena. Okay, what is this? So basically it says, well, initial tokens have large attention scores, even if they are not semantically significant. So if you look at the attention map, okay, starting from, let's say like layer 0 and 1, let's ignore 0, 1, but starting from layer 2, you can see that the initial token, the first token, suddenly have a very high attention score than others. So same for 9, 16, 23, and 31. You can see that the first token always have very high attention score. Okay. Therefore, that kind of explains why, why if you just keep removing it, it suddenly crashes, because somehow we don't know why for now, but somehow the first token has a lot of attention scores. So therefore, as soon as you evict the first token, the model just crashes. So we are going to explain why later, but that's kind of what people observed, okay? So based on this observation, of course, there's a simple fix. What should, like in this case, that there's a simple fix, right? What do you think? Let's try what? So instead of just keep moving forward, we should probably, because the first token has a lot of attentions to it, right? So we should what? Keep it, right? So we should keep the first token. and keep evicting the middle tokens. Does that make sense? And that works actually. So this one also gives you more illustration. See like why the first token, somehow the first token has a lot of attentions. So therefore, and this is explanation why I'm going to explain later. So therefore, one idea is this is streaming LLM. The idea is that if you are processing like a chat like this, what we should do is that we should keep the first token, which they call this attention sink, okay? And then like just keep moving forward. And that works. The perplexity comes back. Okay. And they show that this one has a better accuracy. But then the question is, well, why? Why the first token has so many attentions to it?
It's been seen the longest.
That's one reason. Very good. So because it's been seen the longest, so every token definitely sees token one, right? So that's why it's attended a lot, just accumulated. That's one reason. But that's not the main reason, actually. So people find out the reason for this is that the main reason for the first token, and they tried it. They tried to adding another token before the first token, another just another meaningless token, and people find out that meaningless token is always being attended. What that means is that it's not because the meaning of that token, because when we say like attention, usually it's you attend to a token because it has a relationship with you, right? Like I have like when we do the attention, like we have a high attention score, means that these two tokens are related, right? But now even if you are inserting a meaningless token as the first token, it still gets a lot of attention. Then it means that it's not because it has any meaning in this token. It's because the location, the position of this token. Does that make sense? But why? One reason, as Shofan mentioned, is because it's seen many times that's accumulated, so it has more attention than other tokens. But the main reason is this. Let's say like I have a token, a word like a or the. So this is kind of like a very common word that doesn't have any meaning to it, right? And it does not have any attention to any of other words. What that means that I can delete this word in this prompt. That does not change the meaning of these sentences at all. Does that make sense? So what that means is that this A has nobody to attend to, right? Right? But remember, when we are doing a softmax, when we do a KV cache, when we're doing this KV attention, the softmax requires us what? This softmax requires the distribution of this word's attention has to be summed to what? To 1. Right? Right? But A has nothing to attend to. So what should the A do? Like this meaningless word, A or the, or a lot of other, many other words, like they don't have any, if you delete them, it doesn't change the meaning of this whole sentence, means that it does not need to attend to any of other words, right? But softmax require the attention summation to be 1, right? So what did the model gradually learns that I'm just going to dump a attention 1 to the first token. Does that make sense? Because that means that, you know, usually the first word, everyone sees it. And then like I'm just going to dump my attention, my whole attention to that word. Actually, I can dump this to anyone, right? That doesn't change the meaning of this. But I'm just and then like the model just learns that I'm going to dump my attention 1 to the first token. And this is also like going to be the most stable way of dump the attention, because like, you know, every tokens can dump to that single. Every token sees that token. Okay. So every token can dump my attention to the first token as a safe place to dump my attention. That's why we call this as an attention sink. Does that make sense? Okay. So therefore, in this way, this streaming, I'm basically saying I'm going to keep the attention sink and also the window. Okay. And also like when we are doing this streaming, one thing we need to pay attention is the position encoding assignment. If we keep evicting tokens out and we have a new conversation coming in, we should not, you know, keep assigning this. We should not keep assigning, you know, 6, 9, 10, because if that's the case, then it feels like there's a hole in this context. Okay, so instead of that, we should keep, once you evict those tokens out of this conversation, we should keep assigning like from 0, 1, 2, 3. We should assign 4, 5, 6, 7. Okay. So every time, so basically every time you are entering a new question to the chatbot, you're reassigning the positioning for all those previous tokens. Okay. And also like instead of just keep 1 token, it's keeping the first 4 as the token sinks. Okay. So that's the idea of the streaming, and basically shows it's efficient. Okay, I'm going to skip. Generally, people find out like 4 attention sinks are generally available, but why 4? Because you can see that even if you are using 8 attention sinks, the perplexity doesn't decrease anymore. Okay, but why 4? Can we train a model that you only use 1 attention sink? Yes. So we can introduce a extra learnable token at the start of all training examples to act as a dedicated attention sink. In this way, instead of like using 4 attention sink, we only need to use that learnable token as the attention sink, so to absorb all the attentions. Okay. So attention sinking in other transformers. So in addition to these language models, attention sink also appears in all these vision transformers and the BERT. We are going to talk about vision transformer later. But for BERT, people find out so BERT is it's this encoded structure, right? So an encoder structure. So people find that all the attention sink actually are in this the last token, which is usually it's the sentence separation token. So that's the attention sink. Okay, and for the vision encoder, for the vision transformer, all the model is using all these background information as the attention sinks. This is actually easy to understand. So basically, what an attention sink is, basically it says, well, if this token, if I am a token does not have any relationship with anyone else, then I just need to dump my attention because of softmax to somewhere. So ideally, I should dump my attention to something that's not related to myself. right? Because if I were dumping my attention to something that's related to myself, uh, I'm enhancing my relationship basically, which I shouldn't really should not do that. So that's why for the vision transformer, you are dumping all these attentions to some background pixels. That does not have any meanings. Okay. So this one says, well, can stream large language model streaming LLM give us infinite context? Apparently not. So for streaming LLM, apparently you can keep chat with the bot, right? Without crashing the model. So it still gives you like, but if you think about it, if what you are asking the model said happens to be in the context that's got evicted, then the model has no way to know the correct answer, right? It's not crashing, but the accuracy, when you keep chatting with the bot, the accuracy is going to decrease, right? So that's exactly the problem. So attention is not crashing the model, but as you keep chatting, more and more information in the middle got evicted, the lower, well, you start to see like weird answers. If you ask questions about the previous history, right? So how to solve this? So this is a dual attention as one way to improve it. So dual attention basically says introducing, well, two different types of attention heads. One's called retrieval, one's called streaming. So let's see what it is. So I'm going to skip this. So in dual attention design, basically, we divide all these attention heads into two types. One is called the streaming heads, one called the retrieval heads. Okay, and what they are. The intuition is that when people are looking at the attention map across all these different attention heads, they find two kind of different patterns. Okay, so first, for this kind of attention heads, this head 11 over here, you can see it exhibits a perfect streaming heads pattern. For this attention heads, the most of the attentions are happening across this recent tokens as well as the first token. Okay, but for some other attention heads, it's not. It's attending to the first token. Well, but you can see that the attention across here, which means that the recent conversation is relatively low. And some other, the more important attentions happening in other places. Okay, so the idea is that can we combine both, get the best of both? Okay, so therefore, what it does is that it's going to dividing. I'm going to try to find out. Let's say like I have 64 heads. I'm trying to find out of these 64 heads, which heads are this pattern, which heads are this pattern. Okay, and if ideally if all my heads are this pattern, then I can just use this and it will guarantee to give you good results, because most of the attention are just what that means is that most of the time when you ask a question, most of the answer you can find from the most recent chat history. Does that make sense? Okay, but that's the ideal situation. Most likely it's not. Okay, so therefore I'm trying to find out, some of the heads going to needs information from some of the locations. Some of the heads just need the information from my recent conversation. Okay, so that's the idea. But how do I know which heads are streaming heads and which heads are retrieval heads? Okay, so first for retrieval heads, I'm going to apply the full KV cache. Okay, but for the streaming heads, I'm going to use this lightweight constant length hash for streaming heads because I can keep evicting all those middle content, right? But how do I know like which heads are what? So what it does is that it's assigning a gating um, variable to different attention heads. So I think that this is the illustration over here. Okay, so it's assigning a trainable gate value alpha to each head. So in this particular illustration here, let's say we have two heads. Okay, so I'm assigning alpha to one head, and then like the other head becomes 1 minus alpha. And when I'm doing the attention, I'm going to combine these two attention heads and do the prediction. Okay. Then I'm trying to train the model to learn what the alpha value should be. Here is it. Oh, I'm sorry. I'm sorry. So it's actually here. So I'm going to assign a gate alpha to each attention heads. So each attention is going to, the results is going to be multiplied with alpha and then combined together and to predict the results. But the problem is that I do not know, and if the alpha yes. And then like I'm going to train this model with the loss function over here. This is the training loss function. The loss function has two parts, L distillation and this L regularization. Okay, and let's take a look at what they are. So first of all, this L distillation, what it means is that I'm going to make sure, I'm going to try to maintain the accuracy of the model as much as possible. So I'm compare the accuracy from this model with the original model. So trying to keep the model the same. I'm trying to keep the model accuracy the same. But I'm going to try to minimize the alphas. So on one hand, I'm going to try to maintain the accuracy. The other hand, I'm trying to minimize the computation cost. So, and that is going to that's going to separate the retrieval head with the streaming head. Why? Because the streaming head has a significantly lower computation cost than the full attention head, right? So when I'm trying to minimize the alphas, I'm trying to minimize the total computation operation. The alpha for the streaming head is going to keep decreasing, and the full attention is going to be increased. So in this way, by using this loss function, the alpha for full attention for the retrieval head is going to be big, and the alpha for the streaming head is going to be small. Okay, so in this way, then like I'm going to use a threshold to, if alpha is bigger than the threshold, we say this head is a full attention. If alpha is smaller than a threshold, we say this is a streaming head. Okay, so by doing this, so we can kind of separate the the retrieval head with the attention head. And also, like when you are training the model, we are using this synthetic data to focus on the large language model retrieval capability. What it does is that the synthetic data set is embedded the 10 passkeys in the long context, and we are enforcing the large language model to recall the passkey to identify which heads needs full attention for long context retrieval. Okay, so by using this, we tune the model, can separate the retrieval heads with the streaming heads. So during the deployment, once you can separate the retrieval head with the attention head, during the deployment, all the attention heads are reordered into different distinct clusters for efficient processing. So all the retrieval heads are clustered together, all the streaming heads are clustered together. And for the in the decoder stage, in the decoding stage, for retrieval heads, it's using full attention. For the streaming heads, we are using this attention sync plus the recent tokens. Okay, but during the pre-filling stage, because during the pre-filling stage, you need to process the whole context, right? So for the streaming heads, we kind of like, well, during the pre-filling stage for the retrieval heads, we're still like using full attention. But for the streaming heads, basically we are going to divide them into chunks to further reduce the computation cost. So this one says dual attention does not harm other general capabilities. So this one says within the KV cache, give you higher accuracy. This one shows dual attention increases the latency and reduces the memory usage. Okay, this one compares the again compares the this one shows the pre-filling memory and latency improvement. So combining this streaming LLM, I'm sorry, combining the dual attention with the KV cache quantization, we can significantly improve the processing throughput. Okay, let's take a quick break. Let's say come back at 7:25. All right, let's resume our class. So next we are going to talk about quests, query aware sparsity. So if you still remember this sparse attention, we introduced it before. What it basically does is that like when we are doing this attention, we sum all these cumulative important score, and we are pruning away the tokens that are not important, has lower attention score. That means that like people are not paying attention to them, so they are not important. But the problem with this method is that, well, it's when we say like they are not important, it means that they are not important now, right? But it doesn't mean that they are not important in the future, right? Does that make sense? So therefore, this this history-based pruning method may not work the best. So that's the whole thing that this quest is trying to solve. So this one gives you this example. This sentence, the token, this input is A is B, okay? C is D, and then like it says A is what, right? So if you have this prompt, apparently the answer for this it should be B, right? But the problem with this is that if we were using the previous method, you will find that before you see is over here, token B was not important at all. Because if you look at this, B is not attended with any of these so far. B becomes critical only when we see this is token. Okay, so therefore, if we never see is over here, B is a perfect candidate to be pruned away, right? But then like we have this new question, and then like we have this new question suddenly becomes important. So therefore, we can't just prune away the token based on the history, basically. So in order to do that, fix that problem, the quest idea is this. Instead of pruning the KV cache, the token, we are going to preserve all of it. But then that's going to be a lot of tokens. So in order to accelerate this, the idea is that we only select a subset of the whole KV cache for my current attention. I'm going to keep all of them, but when I have a new token, when I have a new query, I only select the most related keys and to only select the most related pages actually to do the attention. So we are dividing all these KV cache to multiple pages. And every time I have a new query, I only select the most related, most important page. But how do I know which page is important, right? So it's using this estimation method. What it does is that for each channel over here, we are do this reduce the keys. So we calculate the minimum number of this and then the maximum number of this channel. So in this example, for this channel, we have -3 and 4. Okay, and this is -4 and 3. Okay, so for each channel, we just kind of just get the minimum number and the maximum number. Okay, and then I'm going to do a query with this reduce the key. Okay, so I'm going to get this element-wise product. after the query. And then like I'm going to out of this results, I'm going to get the maximum value for this channel. So this one 3, this is 3, this is 12. Okay. And then I'm going to add all these values together to be 39. And I'm going to use this 39 as an indication as to how important this page is. Does that make sense? And then I'm going to pick the top K value of the page. So in this particular example, let's say I'm going to pick page 1, page 2, but I'm going to remove this page N. Does that make sense? So basically the insight is that we should select the page containing the tokens with the highest attention weights. And for the efficient selection of the page, we calculate an approximate attention score. And we find that the upper bound attention weights within a page can be used as a attention score. Okay. So this, with this method, we find that it can achieve nearly perfect accuracy for finding the needle in a haystack. For a super long language model, it has closely matched performance of the full cache model. For the long bench, so the red one is the quest. Okay, so you can see F1 score give you the highest F1 score, the red ones. So quest speeds up the self-attention, speeds up the end-to-end inference as well. So for latency, so outperform the baseline with the same accuracy. Okay. So next, I want to talk about this a alternative to transformer. Okay, so far we have been talking enough of transformers. So called this state space model. So if you look at the transformer, we kind of like, divide this into communication and the computation. What that means is that the attention, the whole goal of this attention is trying to communicate across different tokens, right? So for example, like, I want to modify, like, I want to find out the relationship between these tokens. That's the purpose of the attention. And then this feed-forward network is the one that's trying to decode and generate the result, right? Right. So, but most of the computation, so the state space model, the Mamba, is trying to substitute attention with this state space model for handling sequence communication, achieving linear time processing for long sequences. So this is the Mamba architecture. So you can see that it has this linear feed-forward networks, and we have this SSM. So let's take a look at what is this SSM. So this is the architecture of the SSM. The input is this X over here. So the input is this XT, okay? The output is this YT, okay? And then like, XT has this, going through this BT over here. And the BT is going to adding with the A times the HT minus 1. And what is HT minus 1? Basically, it's the HT from the previous iteration. Okay? And then like, the output goes through the CT, generates the output. So what does this remind you of? This is like what? this is a very popular architecture before transformers, LSTM. Right? Have you guys heard of LSTM? Long short-term memory? Or like recurrent neural network? Okay. So what that does, here's the meaning. So the the H gate, the state H, okay, kind of like keep a memory of the history. Okay. So the H is trying to keep like a memory of the history knowledge. The input X is, of course, is the new information, and the updating is done by this. So the A gate controls how should I forget or update the state over the time. So the A gate will forget some of the information from HT minus 1 and update some information from the BT so I can get a new state, kind of a new memory. Okay? The B gate maps the new input to output. Basically, it says, what part of the new input should I remember? Okay? And the C map is how should I use the state to generate a good prediction. So the long short-term memory thing is that basically means that, well, I have some history memory from previous iteration. Also, I have some new input coming into my memory. So how should I forget some of the old memory? How should I add some of the new memory? How should I combine them together, right? And how should I use them to generate the output? So that's the whole point of the long short-term memory. Does that make sense? Kind of. But if you think about it, if you compare LSTM with the attention, they are kind of similar to some sense. Right? Because attention, initially, when attention was proposed, one of the thing is trying to replace all these recurrent neural networks for the translation, for the language translation. Right? But why? So if you like from a higher level, long short-term memory is trying to remember the history and trying to remember the new data and how they are related and store them into a memory cell. For attention, it's pretty much the same. We are memorize all these keys and the values of all the tokens. And when you are doing attention, because you are basically, the new token is a query, it's asking all the previous histories, saying, are you related to myself? Does that make sense? So therefore, this Mamba is trying to revive this long short-term memory, trying to replace this with attention. And of course, like the benefit is that this is going to give you higher, faster, lower latency. Okay. And the traditionally in long short-term memory, all the matrices, like all the weight matrices for A, B, and the C, they are fixed. So in Mamba, they have a very interesting innovation. Basically says, for my input X, I'm going to do a projection. And this projection is going to be a gate, become a gating mechanism for A, B, and the C. What that means is that now the A, B, and the C, these weight matrices, is going to be depending on this input. When the input is different, the way that how much I should remember, how much I should forget becomes different. Does that make sense? Which kind of give you this attention idea, right? So give you this. So for example, without selectivity, the memory kind of remembers like I want to order a burger, okay? But once adding this blue lines here, all these blue lines here, kind of trying to select based on my current input, I'm going to allocate more weight to the important tokens based on my input. Okay, so that's kind of interesting innovation. So this one says how to accelerate. But with the selectivity, it's very kind of hard to train the model. So they propose this linear parallel scan algorithm to kind of how to train this model. So to train a model with the LSTM, we have something like this, right? X0, H0, X1, H1. And this is a sequential model. And we know that to train this model is actually quite time consuming, right? So they propose something called, not proposing, they are basically borrowing this parallel scan algorithm from a old paper, really old paper. So the parallel scan idea is this. Well, let's ignore this this Mamba architecture. Let's just looking at these numbers. If I want to add a summation of these numbers, traditionally I need to do this: 4 and 4. Then 4 plus 1 equals to 5. 5 plus 5 give you 10. 10 times plus 3, 13. So therefore, this calculation is strictly sequential, right? So the parallel scanning idea basically says, well, I don't want to wait for the previous ones to finish. So basically what it's doing is that I'm going to do 4 plus 1 give you 5. At the same time, I'm going to do 5 plus 3 give you an 8. And 9 plus 2 give you 11. Okay, and then I'm going to add 5 and 8 to 13, and 9 to 11. So finally, 13 plus 11 give you 24. So as like a binary kind of search idea. Does that make sense? The same thing when we are training this model, we are doing it similarly. We are going to combine x1, x0 first, 2, 3, 4, 5. So we're doing this in parallel. So this one kind of speeds up the calculation process for this sequential process. Okay. And the hybrid, finally they have this hybrid transformer Mamba language model. What they do is that they are alternating this Mamba layer with MOE, Mamba layer and Mamba layer MOE, and with the transformer layer. So they are alternating all these, connecting all these layers together. Okay, and they find it gives you a good performance. Okay, so that's how people are trying to, instead of like keep accelerating the transformer, we want to just replace the transformer, part of the transformer with the Mamba architecture. So if you think about it, what is the benefit of this? So we know that for Mamba architecture, this is a sequential model. It means that it can take any length of the input because it's a recurrent network. No matter how long it is, I'm just keep running itself. Does that make sense? But the drawback of the Mamba is that this recurrent neural network, the memory is a compressed memory. It's a lossy memory, right? So it can take any length of this context, but I can only kind of have a compressed memory of the history. On the other hand, the attention is the lossless. The whole sequence has the keys and the values. I can always go back and find the relationship, right? So this one kind of trying to combine these two different ways to have a balance between the accuracy and the efficiency. Okay. So that's all for this lecture. So recap. In order to tune a model, tune a large language model that was trained with a fixed small context window size, let's say 248 or 496 token size, to accept a much longer context window, we need to tune the model, right? We need to fix the positioning and encoding problem. We need to tune the model with the longer context, okay? And we talked about how to evaluate these models. And then we talked about, when we are processing streaming chats, how to do this attention sinks, okay, and how to evicting the previous tokens. And then we talked about how to combine dual attention, how to combine retrieval heads with the streaming heads so that we can, reduce the memory requirement, but also keep a good performance. Then we talk about this query quest, how to store all the cache, but only use part of it when we need it. Okay. And then we talked about, we did so many things to optimize the attention process. How about we are trying to replace the attention with something else, with a long short-term memory, like called this Mamba. Okay, and then we talk about how to combine Mamba with the transformer to have this hybrid model, this Jumba, to have good performance as well as have good latency and accuracy. Okay, again, this is all for this super long context window.